Hey everyone, this is Dr. Walker. This is video 103C, Keplers Laws. A very brief history. In the late 16th century, the astronomer Tycho Brahe compiled observations of stars and planets for about 30 years. And it was his assistant, Johannes Kepler, who analyzed the data and discovered the three laws that we call Kepler's Laws. These laws describe the planetary orbits around the Sun. The notion at the time was that the Earth was the center of the solar system, if not the universe. There were some heliocentric models, such as Copernicus's model, that showed that the Earth was revolving around the Sun, but it showed circular orbits. So Kepler's laws had much better descriptions for the orbits of the planets. The first law states that the planets move in elliptical orbits with the Sun at one focus. The only thing you really need to know about the elliptical orbits is that you do have these axes called the semi-major. This is the semi-major axis, and which we call A, and this other one here is the semi-minor axis. And so those two axes definitely describe the shape of the ellipse. And then the quantity that we use to describe the shape of the ellipse is called the eccentricity. And it's defined as the ratio C over A. C is the distance from the center to a focus point. So the eccentricity can be between 0 and 1. If it's 0, that means that you have a circle. If it's 1, that means you're going to have a very elongated ellipse. So although the Earth and the other planets have elliptical orbits around the Sun, they actually look very circular. The eccentricity of Earth's orbit is 0.017. The planet with the highest eccentricity, which is Mercury, has an orbit of 0.21, but the orbits still look very circular. Now, if you look at the comet Halley, for example, then that eccentricity is 0.97, and that might look more like an ellipse that you think of. So that was the first law describing the shape of the orbits of these planets around the Sun. The second law states that the radius vector to a planet sweeps out equal areas in equal time intervals. So what does that mean? Well, all that means is if you have a planet that is moving from here to here, then you can look at the area that is swept out by the radius vector as it goes from one position to another position. It sweeps out this area. So if it sweeps out equal areas in equal time, that means that when the planet is closer to the Sun, let's say it's over here, let's say it's moving this way, well, however long it took to go from here to here, whatever that area is, it's going to sweep out that same area, and I'm just approximating that this area is the same as this one. That means it's going to go from here to here in the same amount of time that it took to go from here to here. This law is a result of conservation of angular momentum. I won't go into the details of this derivation, but the result of using conservation of angular momentum, we see that the area swept per time is the angular momentum divided by 2 times the mass of the planets. And since all of these are constants, it shows us that the area swept out is constant, no matter where you are around the Sun. Let's look at a question. A satellite has an elliptical orbit with the Earth at one focus. Which statement is true about the satellite's speed at point A and point B? So this question is going to tell us a direct consequence of Kepler's second law. Can you figure it out? So when the planet is at point B, right, however long that is orbiting, the area swept out is going to look like this. When it's going to point A, the area swept out looks like this, right? Well, from wherever it starts, but we know that the shape looks like this. So when it's at A, it has to be going a lot faster than when it's at B. Because look, if it covers from here to here in the same amount of time as it covers from here to here, well, there's much less distance traveled here than here. So more distance traveled means that it's going faster. So when the planets orbit around the sun or satellites orbit around the Earth, if you have an elliptical orbit, the speed is not uniform. The satellites or the planets, they do orbit faster as they are closer to the object that they are orbiting. So the speed at A is greater than the speed at B. Let's look at Kepler's third law. It says that the square of the orbital period of any planet, remember the period is how long it takes to go around the sun or whatever it's orbiting, is proportional to the cube of the semi-major axis of the elliptical orbit. This law I do like to derive because it's a relatively simple derivation. It comes from understanding that the orbit, let's say, of this planet around the sun is due to the gravitational force, right? This gravitational force acting on the planet is what provides the centripetal force that allows it to move in nearly a circle. It is an ellipse, but it's nearly a circle. So what we do is we say that the gravitational force provides a centripetal force, and we write down the equation for gravitational force, and we write down the equation for centripetal force. And then we plug in the definition that V is equal to 2 pi r over t. So that makes sense, right? The speed of your planet is the distance, the circumference divided by the time for that one revolution. So when you plug that in, and then you do the math to solve for the period, that's how we get this law. Now this is for a circular orbit, but it generalizes to an elliptical orbit by using the semi-major axis instead of the radius. A very cool significance of this law is that it definitely allowed scientists and astronomers to gather information. If you know the time that it takes for a planet to orbit a star, then you can figure out how big its orbit is. But also, if you have information about a planet's the time of its orbit and the size of its orbit, then you can actually get information about the object that is being orbited. So if you know how long the Earth takes to go around the sun and you know the size of Earth's orbit, that allows you to figure out the mass of the sun. We'll do that in an example in the following video.